So let's just quickly look at the factors that can affect the number of successful collisions. We're going into reaction rate just now, and we'll look at reaction rate that, and I'll explain it. But let's just see what things can affect the number of successful collisions per unit of time. Like every second there's so many successful collisions. What could affect it? Well, the two things we've already looked at, actually three things because you mentioned it, was a catalyst. Will a catalyst always work or only in certain circumstances? What do you think, Melina? It will always work because you're reducing the activated complex. If you reduce the activated complex, it doesn't matter what, it doesn't depend on the substances. It only depends on the activate. So the catalyst is actually affecting the very energy level needed. So catalyst will work for any situation. So in other words, if they ask you, recommend what can be done to increase the reaction rate, then in other words, if they ask me to increase the reaction rate, they want me to have more successful collisions every second. And then I said, well, I can add a catalyst always. So catalyst is always an answer. Temperature. We looked at temperature. What does temperature do again? Catalyst reduces activated complex. Temperature. It increases the average kinetic energy of the molecules. So will a temperature always increase the reaction rate? In other words, will it always cause more successful collisions per second?
If it is increased.
Yes. True. Okay, so if it's increased, it will always increase the number of successful collisions. Let's call it SC, successful collisions. Okay. Then we looked at pressure. Will increasing the pressure always work? There's something inherent when we talk about pressure. It can only work for gases, because a gas is the only thing whose pressure I can change. I can only decrease the area for a reaction if the reaction actually contains gas. Okay, for example, how do you increase the pressure for two fluids that are being reacted? Okay, you can't. So increasing pressure will always work for gases. So you can only recommend increasing pressure if one of your reactants is a gas. And then what else? What would be the equivalent if I was working with liquids? What is the equivalent? Well, I'll tell you guys. It's concentration. Okay, so when we have liquids, usually that react with one, and it's not always the case that we use concentrations, but for example, if I wanted to do a titration, you guys know that a titration is where I use an acid to neutralize a base, or base to neutralize an acid. We don't use pure acid and pure base. We dissolve them. Okay, we use concentrations of the one and a concentration of the other. Okay, one reason why is because some acids are just too strong to keep in a container. Because so in other words, to keep them in a container, we need to actually use concentrations of them to actually keep them. So we can't always use a pure substance. So especially in liquid form, some things that I might want to react. So for example, I might want to react salt with something. And so, for example, even on your food, to salt your food, the salt needs to dissolve in order to salt your food. Okay, if it didn't dissolve even in your mouth, you would never have tasted it. Okay, so salt needs to dissolve. Now, so what would increase? So let me give an example here. So here is, for example, my liquid, and not 100% of my liquid is pure substance. The rest might just be solvent. Okay, so the concentration is the relationship of the moles of substance divided by the volume of my solvent. Okay, so not N. Okay, this is concentration. The mole of substance divided by the volume of my solvent. Now, just imagine that these little dots represents the number of product that I actually want to react. If I now have another product that is also being dissolved in here, a reactant that's being dissolved in here, okay, do you notice that the space between the molecules are fairly big? So the chances that as the molecules are moving around, they miss each other is high. So if I want to increase the probability of a successful collision, I need to increase the moles, the number of molecules that I actually have in here. So by increasing concentration, I'm again not increasing the kinetic energy, but I'm increasing the probability that things that already have enough kinetic energy will actually collide. Does that make sense? So an increase in concentration. So when will an increase in concentration increase the number of successful collisions? When I'm working with aqueous solutions. That's not how you spell aqua. That's not how you spell it either. In aqueous solutions. So that is if there's in your reaction formula there's an AQ. Then you're going to use that.
That'd be the same as when you just put an L.
A liquid isn't a concentration, it's a pure substance, so you can't increase the concentration in the liquid. Okay. So it's only when they literally say they have something, and they say, so often we would have that we have, for example, an acid, and then they put AQ, which means it's not a pure acid, it's been dissolved probably in water. Okay. And the final thing is surface area. Now, a good example of this would be just looking at if you have water here, and in the water you put a steel nail. Okay, now that would be iron plus water, H2O. Iron is a solid, water is a liquid, and it will produce iron oxide, I think it's FeO, plus hydrogen. Okay, It's a very slow reaction. Rusting is very slow. You don't see it immediately, but a day or two and you see something that's been lying in the rain or something like that has rusted. But if you were to take the same... Now, so again, why does this happen? Because the water molecules collide with the iron. But the water molecules can't collide with the iron that's on the middle of the nail. In other words, the molecules right in the center of the nail, or even the molecules that's just underneath the surface. It can only collide with the molecules on the surface of that nail. Do you notice that? So, for example, if I were to take this little block, okay, and let's say it's a meter by a meter, or let's not say meter but unit. It's a meter there, and a meter here. So 1 by 1 by 1 deep. Okay, this is 1 cubic meters, and again, that's a massive block. But now look at the surface area of this thing. If I all of a sudden halve this thing so that I have 2 of them, and let's say that here where I cut it, this is the area where I cut it. Okay, that's the 2 faces that used to be on top of one another. These 2 faces is now a meter by meter. So sorry, this I worked out when I did the volume. It's not the volume. This cube originally had 6 sides. Each side had 1 by 1. So the area of each side was 1 square meters, 1 times 1. So it had 6 sides. So if I add all 6 sides area, I would have a total of 6 cubic squares. In other words, on those 6 cubic squares, all of the molecules on the surface would be able to interact with the water molecules as they collide. Does that make sense? But now, once I cut it in half, now all of a sudden, I have all of the surface area that I had initially is still exposed, but now these 2 sides that didn't used to be exposed is now exposed. So by doing that, I all of a sudden have 8 cubic meters that's exposed to the air or to whatever the surrounding environment is. Okay, so by increasing the surface area, and how do I increase surface area? I break whatever solid I have into smaller pieces, because each time I break it, the part where I broke it, what is now inside, that is now exposed to the outside. So if I break it again, I've got more surface area that's exposed. So obviously the best possible way is to actually grind something into a fine powder, because then you've actually exposed as much as possible surface area. So the finer you ground it, the more surface area you are exposing, even though it doesn't look like it, but it literally is. Okay, so do you understand? So if I were to take this nail and I were to somehow grind it into a fine powder, you would actually, even within a few hours, be able to see the rusting happening, because of the probability of successful collisions. So surface area is only used in solids by increasing the surface area. And how would we do it? We either break the thing into smaller pieces or grind it finer. So there's 3 ways to increase successful collisions. Remember, a successful collision means that my potential energy is less than my kinetic energy. That 2 molecules, and this is the theory, this is what they think, how it's happening, is that molecules are moving and colliding with one another, and some of them have enough energy when they collide to actually break the bonds and form new bonds. Okay, now that means their kinetic energy is more than the potential energy. Now if that's the case, there's 3 things I can do to increase the number of successful collisions. I can either decrease the amount of energy needed. In other words, I add a catalyst. Or I can increase the amount of energy that the molecules have. How do I do that? How do I increase the kinetic energy that they already have? Temperature. I increase the temperature. To be honest, temperature is, when you add temperature to something, it is just the motion of molecules. Okay, you're increasing the motion of molecules. That is what heat is. Okay. The third thing is you can increase the probability of a successful collision by decreasing the chances of unsuccessful collisions. That's kind of what you're doing. No matter what you're working. How do I decrease the chances of unsuccessful collisions when I have gases? I'll just take away space. So I'm increasing pressure or decreasing volume. Okay. How do I do it in a concentration? Or in an aqueous solution, I just increase the concentration, meaning that I'm increasing there's less solvent in there. That's the idea. There's less solvent because there's no successful collisions when the one molecule collides with a solvent. It's when it is colliding with the active ingredient. And then if it's an area, how do I decrease chances of unsuccessful collisions? I expose more of the surface area because the molecules are very snug on the inside, so I expose them to the actual surface that's in contact with the other reactant. Make sense? Yes. Makes a lot of sense. Good.